Okay, so I want to just point out some things in the ebook here for Appendix H.2. So these polar coordinates, these polar graphs are great, but you maybe even yourself wondered, looking at that four-leaf rose, hey, what could we find the area of one of the leaves? I mean, that's an interesting idea, right? And the answer is yes, you can. And H.2 talks about how to do that kind of thing. All right, so I'm in polar coordinates right now. Look at some of these polar graphs. Look at that. Isn't that incredible? This is actually figure 17 from section H.1. All right, let me see here. Just got to get to H.2. A little slow. Okay, areas and polar coordinates. All right, so this is section H.2, figure 2. The scenario we're dealing with now is we have a polar curve given by r equals some function of theta, and our starting limit and ending limit are angles. Because r is a function of theta, we're going to integrate with respect to theta. Well, that means you're integrating with respect to angles. So there's a starting angle at theta equals A and an ending angle at theta equals B. And you know that those are just the graphs of theta equals A, theta equals B. And we're interested in what's the area under the polar curve between the angles of theta equals A and theta equals B. So in order to do this kind of problem, you have to treat it just like you did when you learned about integrals with respect to x, and you took your area under the curve and you broke up the area into a bunch of rectangles. Okay, it's the same kind of principle here. I don't know how I got moved. It's the same kind of principle, but what you're doing now is you're breaking up the area under the polar curve, r equals f of theta, into sectors. So you're taking a bunch of different angles, and then between two angles is a sector. And you can approximate that sector by the area of a sector of a circle. And I know it's probably been a while since you've seen that, the formula for the area of a sector of a circle, but the area of a sector of a circle is 1/2 r squared theta. Okay, how many remember maybe seeing that for the area of a sector of a circle, it's proportional to its central angle. So area equals 1/2 r squared theta. Has anybody maybe seen that in pre-calculus, in their home schools, or I'm not sure how well it's covered, but well, it makes sense because I mean, just think about if theta were equal to 2 pi. the area of a circle, an entire circle, is pi r squared. So if you put in theta equals 2 pi here, you're going to get pi r squared. However, if you're interested in half the circle, the area of half the circle is 1/2 pi r squared, and you just put in theta equals pi. So the area of a sector is proportional to its central angle. But the point is, the area of a sector is 1/2 r squared theta. And so now, if you're trying to find these, when you divide the area under the polar curve up into these sectors, these circle sectors, the radius is dependent on the angle. So that's, and then the radius is equal to f of theta. Okay, right? And the area of each little sector is going to be 1/2 times f of theta squared, which is the radius squared approximately for that sector, times delta theta. Delta theta is I'm going to say it the right way. It's the difference between the two angles, the beginning angle and the ending angle, that form that sector. Okay, it's like the little piece of the pie, right? So therefore, an approximation of the total area is going to be the Riemann sum, where I equals 1 to n, of 1/2 f of theta I squared delta theta. And of course, as you take the limit as n goes to infinity, in other words, if you take the sectors of the underneath the polar graph and take more and more of them, your approximation is going to get better and better. And so the area is going to equal then the approximate area under the polar graph from theta equals a to theta equals b will equal the integral from a to b will times f of theta quantity squared d theta. So the Riemann sum here, the Riemann sum turns into the integral. And this gets you your formula. Are there any questions so far? So that's what we get in formula 3. Area equals the integral from a to b 1/2 f of theta quantity squared d theta. But remember, f of theta, we set it equal to r, right? So we can rewrite formula 3 as the area equals the integral from a to b of 1/2 r squared d theta. Okay, so normally the hardest part of these problems is figuring out the beginning and ending angle. Or I should say it's one of the harder parts of the problems, but you know, you'll get better and better. So now we have this formula, okay? The area equals the integral from a to b 1/2 r squared d theta. That's the formula for the area of a polar region where your angle limits are starting at angle theta equals a and going to angle theta equals b. If there are no questions on that, I'll try to get to some examples. Are we good so far? Okay. Polar coordinates, by the way, are very important. They're very important in applications, but let's just continue here into the examples. So let me stop sharing there, and let me see. Okay, so here's the first example. Find the area of the shaded region where r equals 4 plus 3 times the sine of theta. Let me give you a moment to copy that example down. And I should mention, you're wondering, well, what is the shaded region? Let me draw it for you here. This is called a cardioid, by the way. Because it looks like a heart. It looks like a heart. It's called a card. And just cardioid. Hope I'm spelling that right. Hold on. I think I am. There is no E here. Nope, no E. And the shaded region I'm interested in is to the right here. Just the right half. So Natalie, let me ask you, how do I get, now how, if you had this on the homework, how would you produce this cardioid graph? How would you produce it? How would you do it? What's a quick way to get the graph? Use the calculator. So I agree, Josiah. I would use the calculator, and if you want, take a moment to type in 4 plus 3 times the sine theta on your calculator. You can pick an appropriate window. You should get something, a graph that looks like that. I'm not really interested in right now in terms of, like, what I mean is that, like, you'll have a problem like this in your homework, and the problem gives you a picture because they're not interested in having you spend time drawing the graph. They just give you the graph. But the question is now, what are my beginning and ending angles? What are my beginning and ending angles? So, because I know I have a formula to find the area of a shaded region. Okay, this is the pole. I mean, this here is the. Let me maybe make it maybe in black. This here is the polar graph, right? This here, starting here, and hold on here, and ending here, right there, is the polar graph. So for my starting angle is this angle here. Whoops, hold on, let's make that in green. This is my starting angle. Okay. The graph actually does, you know, it is like vertical here. Okay, so my starting angle is in that direction. What direction is my starting angle? In the green. The green angle in that direction of the green line, am I looking up or am I looking down? I'm looking down, and so that's right, John. This here, very good, is theta equals negative 90 degrees. Are there any questions on that? I haven't made a table of values or anything like that. All I need to know is where the graph, for what angle does the graph start, you know, and for what angle does the graph end, finish. Okay. The only part of the graph I care about is the right-hand part of the graph. So now the other angle, we'll just be a little bit careful here. Put that up like that, okay. The other angle is here, right? Okay, so the graph ends here, and this angle, well, we're looking up. What theta goes with that? Pi over 2. That's right, John. 90 degrees. So you have your starting and ending angle. Okay. Are there any questions so far before I move to the solution? Everybody has the picture okay? Okay. So let's go then to the solution here. Okay, and I know that my notes are a little, well, these are fine, the notes. They're a little messier than I've had in the past just because I really wanted to get the exam done. So I stayed up pretty late getting it done. It takes some time to look over your work. So this part, here's the solution right here. So these notes are a little bit unpolished, but still readable. So the area is going to be 1/2, the area is the integral of 1/2 r squared d theta, and theta goes from negative 90 degrees, right, negative 90 degrees to 90 degrees, and it's just computation. So, of course, I'm going to do FOIL here. I have 4 plus 3 times the sine of theta times 4 plus 3 times the sine of theta. When I expand that, that's going to get me this integral here. Maybe I'll start writing in blue here. Okay, let me know, are there any questions? Okay, all right. So, okay, one moment here. So now, with integration with polar equations, we want to do anything that's going to make our life easy. So I know that I could write, of course, the 1/2 I bring out front here. And I know I have the integral of the sum of 3 functions. So I could write that as the sum of 3 integrals. But in terms of the 24 sine theta part, I know that the sine of theta, if I graph the sine of theta, okay, it is an odd function. It's an odd function. And so being our limits are from negative pi over 2, negative 90 degrees, to pi over 2 to 90 degrees, the area of 24 sine theta, okay, the area underneath 24 sine of theta, that function from negative pi over 2 to pi over 2 should be 0. So that means we can just eliminate that term. We can eliminate it. And so I have then the 1/2 times the integral from negative pi over 2 to pi over 2 of 16 plus 9 sine squared theta. Okay. All right, one moment. Now we have to justify the next step. But what I'm doing here, I'm just, so 16 plus 9 sine squared of theta should be symmetric with respect to the y-axis, because the sine squared it's like if you take well, it should be an even function. Our limits go from negative 90 degrees to 90 degrees. That means, or negative pi over 2 to pi over 2. So zero's right in the middle. The y-axis is right in the middle. So if you were to let me just see here, graph this 16 plus 9 sine squared of x. Let me just check one thing here. One moment. I might bring up the thing so you can see this. One moment. Yeah. What I'm going to do is this 16, I want to justify how I'm going from this step here to this step here. Okay, where I've replaced the bottom limit with negative pi over 2. I've replaced it with 0, and I have a 2 here. So just give me one moment here. I'm going to come back to this, but I want to graph 16 plus 9 squared of theta on the calculator from negative pi over 2 to pi over 2. Okay, so let me do that, and I will make it visible for you as well. There might be a little error there in the integram, but we'll worry about that in a moment. Okay, so 16 plus 9 squared. Let me go into my application. Now what I want to do is I want to just graph like a function, because what I'm trying to do is see if this function should be symmetric about the y-axis. Okay, but I'm just trying to show you, rather than just say it is, I want to show it to you. So I took my calculator off polar mode, and I'm typing in 9 plus 16 sine squared of x. Again, I'm just testing to see, I'm just trying to show you this is an even function. So what I'm going to do is I'm going to write my limits from pi over 2, negative pi over 2, sorry, to pi over 2. Since my angles are from negative, my two angles are negative pi over 2 to pi over 2. And then for the scale, well, this one I can just sort of, I'll just use pi over 4. And it's clear that this function is going to be positive But because of the 16 there, the function's going to be, the 16 and the 9 are going to make the function get big. So maybe I'll do like 25 here and 5 there. I'm just going to use an appropriate window to graph my function. Are there any questions so far? Okay, so let's graph it. There we go. So this 16 plus 9 sine squared is clearly an even function about the y-axis. Okay. So that means then, is everybody okay with this? Are there any questions so far? Maybe give me a thumbs up if you're comfortable so far. Is everybody okay on the graph? So again, what I'm trying to do is establish to you that 9 plus 16 times the sine squared of theta. I want to show you that that is an even function with respect to theta, with respect to the vertical axis. Theta equals, I got to be careful here how I phrase this. Okay, let me phrase it another way. So I graphed y equals 19 or y equals 16 plus 9 sine squared of x, right? So y is the vertical axis, x is the horizontal axis. But I could instead say, hey, let my horizontal axis be theta, okay, instead of x. Well, the 16 plus 9 sine squared of theta graph is symmetric about theta equals 0. So that means to the right of theta equals 0, the area under the curve is the same as the area under the curve to the left of theta equals 0. So rather than have my limits going from negative pi over 2 to pi over 2, why don't I just change my limits from change my limits to theta equals 0 to theta equals pi over 2, and take that area to the right and just double it. And that should equal the entire area from negative pi over 2 to pi over 2. That's what I'm doing here. And so then, if we get back to the example here, okay. So this integral here then will equal 2 times the integral, okay, 2, this is a 2 out in front here, this is a 2. Let me do it again. This integral here will equal 2, okay, and maybe make it will equal 2 times this circled integral here where the limits go from 0 to pi over 2. I do not think the 1/2 should be there. I do not think this 1/2, let me just double, all right, so let me let you absorb that for a minute and check on one thing here. Yeah, this 1/2 here should not be here. This 1/2. Okay. So are we okay going from this? Are we okay going from the left integral to the right integral? And again, I wanted to justify why we can do that. It's because this 16 plus 9 times the sine squared of theta is symmetric about theta equals 0. And the reason we want to, this is helpful, is because it's easier to integrate and evaluate the function at a value of theta equals 0 than a value of theta equals negative pi over 2. All right, maybe give me just a thumbs up, and maybe just a few of you, if you're at least, I mean, are you okay? Are we all right? Thank you, John. Thank you, Robin. Excellent, excellent. So now comes the integration part. Okay? And I'm gonna like, here, well, okay. So the sine squared of theta, we have to replace that with an identity. The identity for the sine squared of theta is 1/2 times 1 minus cosine of 2 theta. How many have seen that trig identity in their trig class? That's right. John has. Anybody else? Hopefully more of you have. So sine squared, thank you, Robin. Thank you, Francesca. Excellent. So sine squared of theta equals 1/2 times 1 minus the cosine of 2 theta. And so that will end up equaling 41 pi over 4. So like, I'm not going to, this integral here, I mean, I'm not using limits from negative pi over 2, so I can let that one, I can just cross that out. But now you just do the math, you do the integration. You can integrate 16. The antiderivative of 16 is 16 theta, right? Maybe I can fill in the last step. 16 theta. And then you're going to have plus 9/2, because you have that 9 there, times, I'll finish the integration here with you. 9/2 times theta minus the sine of 2 theta over 2. It's just simple integration. Now, one more thing. We do have the 2 times 1/2 here, but that equals 1. Okay, so limits go from 0 to pi over 2. So I'm doing live integration here. Hopefully it'll work out. It's always embarrassing when it doesn't, but I have I hope to get 41 pi over 4, but are there any questions so far? All right, so I'm going to take 16 times pi over 2 plus 9/2 times pi over 2 minus the sine of pi, because 2 times pi over 2 is pi, all over 2. Okay. And when I put 0 in for, then I'm just going to get a big old 0 here. If you put 0 in for theta, you're going to get 0 everywhere. And the sine of 2 times 0 is the sine of 0, and that's 0. So you see, that's an advantage of rewriting the integral in this form, because the angle 0 is easy. Okay, so we're going to get 8 pi here. 16 times pi over 2 is 8 pi. And then 9/2, sine of pi is 0. 9/2 times pi over 2 is 9 pi over 4. I guess I don't need to be this tight here. Hold on, let me write it down here. Eight pi plus 9 pi over 4. Okay. Plus 9/2 times 0, right? Because the sine of pi is 0. But 8 pi, and just ignore the phone. One moment here. Eight pi is the same as 32 pi over 4. I'm feeling good here. And it works. We get 41 pi over 4. And that's what WebAssign is going to want. It wants exact values. It does not want decimals, and I don't want decimals. So for your final exam, these kind of problems, you need exact answers. Decimals are kind of a cop-out, right? When you can get the exact, beautiful answer, why would we want a decimal approximation, right? Okay, are there any questions on the work here? Is that clear? So I broke it down into this step. And this step. And finally this step. and we got 41 pi over 4. How many think that's absolutely cool? Thank you, John. Thank you, Robin. All right, are there any questions at all? So when you do these problems where you're integrating you're finding areas underneath polar curves, you always want to think about these kind of shortcuts if you can. Notice that we utilized two shortcuts here. First, we recognized that 24 times the sine of theta is an odd function with respect to theta, and since our limits were from negative pi over 2 to pi over 2, we were able to, we don't need to worry about that term. And then we took 16 plus 9 sine squared of theta and found that that function is symmetric about theta equals 0. So that allowed us to rewrite the integral in this nice form here, where we just double the area under the curve from 0 to pi over 2. So these little observations when you're doing your integral can be helpful. So sometimes these kind of problems, the H.2 problems where you're computing area, before you just sort of rush to complete the integral, it helps sometimes to take a pause and see if there's anything you can do to make your life a little easier. All right, let me stop the recording.